Okay, so this is my second video of the day for today, and I said I was going to focus on the standard approach. Okay, so for the standard approach, I'm going to be using the standard notation also. And before I talk about the standard approach, I want to remind you of the first principles. So during the first principles approach, we said dy dx, which is our gradient, is going to be given by limit as delta x approaches 0 of f of x plus delta x minus f of x, everything over delta x. Much as this gives us the differential, I think from the questions that we've encountered, we've discovered that this is not always easy to calculate. Okay, it's very easy if I'm going to be having maybe a term where you're going to be having, say, x squared. Then you can have x plus delta x squared, and then if I have f of x is equals to x cubed, then I can have x plus delta x cubed, which is not actually an easy way to, or an easy thing to calculate. So we have to look for an alternative method, and this alternative method is what I'm actually calling the standard approach. Okay, so using the standard approach, this standard approach uses conclusions from the first principles approach and makes generalizations for situations. So if you do a lot of this, you discover certain patterns and certain generalizations, which I'm going to be writing down here. So the first one is, if you have y is equals to a to the power of x, sorry, a times x to the power of n, where a is a number, okay, and n is a number, then dy dx is going to be n multiplied by a multiplied by x to the power of n minus 1. Okay, let me give you examples. E.g., if I have y is equals to x squared, then dy dx, the derivative function for this, is going to be 2 multiplied by x 2 minus 1, which is literally 2 multiplied by x. 2 minus 1 is 1, so that's 2x. All right, which is a faster way of differentiating than this. However, your syllabus requires you to know this. Much as we have this faster way, we should also remember this first principles approach. Now, another example, if I have y is equals to x cubed, then dy dx will become 3 times x 3 minus 1, which is 3x squared. Okay, so what I'm literally doing is I'm dropping the power and then I'm subtracting 1 from the power in order to differentiate every x term that you see, because this is saying with respect to x, so x is our variable, so I am going to be dropping the power and subtracting 1 from the power. Then I'll have my new statement. Another example, y is equals to 2x to the power of 4. Therefore, dy dx is going to be equal to 8. That's 2 multiplied by 4, it's 8. X to the power of 3. 4 minus 1 is 3. So that's what you're supposed to be doing every time you see x to the power of n. Then the derivative, if I see x to the power of y is equals to x to the power of n, then the derivative is n times a times x to the power of n minus 1. Right. Thank you.